this module, you will learn about subsets, supersets, parsets, and universal sets. Suppose we have two sets, A and B as shown. The elements of set A are also present in set B. So, we can say that the elements in A are contained in B. In other words, we can say that set A is a subset of set B. This is symbolically represented as shown. This symbol represents subset. We can say that a set P is a subset of set Q if every element of P is also an element of Q. Symbolically, the definition of the subset can be represented as shown. The highlighted symbol denotes the word implies. This statement is read as follows. P is a subset of Q if X is an element of P, which implies that X is also an element of Q. If a set P is not a subset of set Q, we can represent this with the help of the symbol shown. If every element of set P is contained in Q and vice versa, then sets P and Q are equal. If every element of set P is present in set Q, we can say that set P is a subset of set Q. We can also say that set Q is a subset of set P. Therefore, set P and set Q are equal to each other. This can be defined symbolically as shown. The highlighted symbol means if and only if. The next observation is that every set is a subset of itself. This is symbolically written as shown. The third observation is that if a set A is a subset of B and A is not equal to B, then A is called a proper subset of B, and B is called the superset of A. If any set P contains only one element, then P is called a singleton set. An empty set is a subset of every set. Since an empty set has no elements, it is a subset of every set. Now, let's observe some sets built using the elements of a given set. We have a set of elements as shown. Let's form new sets with a combination of the elements in this set, taking one element at a time. We have these sets. Taking two elements at a time, we have these sets. Taking three elements at a time, we get this set. Taking 0 elements at a time, we get a null set. All these sets are the subsets of set S. We form a set with the newly formed sets as its elements. This set is called the parset of set S. This set is denoted by P of S. The number of elements of this set is 8. We can say that if a set S consists of m number of elements, the number of elements of the parset is equal to 2 par m. The collection of all the subsets of a set A is called the power set of A. It is denoted by P of A. In P of A, every element is a set. Let's see an example of a power set of a set B. Taking one element at a time, we get these sets. Taking two elements at a time, we get this set. Taking 0 elements at a time, we get a null set. Taking these sets as the elements for a set, we get the power set of set B. The number of elements in set B is 2. The number of elements in the power set of B is equal to 2 square. That is 4. In some situations, we may have to identify sets based on the context. Consider a set of natural numbers. This set is a part of another set. That is, the set of real numbers. In this context, the set of real numbers is the universal set. Similarly, for the set of integers, the universal set is the set of real numbers. Let's take another example. Any plane figure, such as a circle or a square, is made up of points. We can say that for all plane figures, the Euclidean plane forms the universal set. Let's apply the idea of subsets in the context of real numbers. We know that integers, natural numbers, whole numbers, rational numbers, and irrational numbers together form real numbers. In set theoretical representation, we will explore how these sets are represented. The set of natural numbers is a subset of whole numbers. The set of rational numbers is a subset of the set of real numbers. The set of numbers we have seen are well known to us. We will see some conventions that will help us to understand sets that consist of any number of elements on the number line. On the number line, each point represents a number. For example, let's consider the real numbers in the interval between the numbers 2 and 3. 4 types of intervals can be considered with these 2 points as the endpoints. The first interval includes the numbers 2 and 3. This interval consists of all the numbers between the numbers 2 and 3. In set builder notation, the interval is represented as shown. The second interval is all the numbers within the interval 2 and 3, excluding the number 2. This is represented in set builder notation as shown. The third interval is all the numbers within the interval 2 and 3, excluding 3. This interval is represented in the set builder form as shown. The fourth interval is all the numbers within the interval 2 and 3, excluding 2 and 3. This interval is represented in the set builder form as shown. Of these sets, the set including the numbers 2 and 3 contains the greatest number of elements. With the observation, we can define some sets of real numbers. The interval 0 to infinity, with 0 included, is the set of non-negative real numbers. The set shown defines the set of negative real numbers. The set minus infinity to infinity defines the set of real numbers. On generalizing, we can conclude that the set of real numbers in the interval between two numbers a and b, including a and b, is defined as shown. Similarly, other sets of real numbers are shown. For all the intervals shown above, B minus A is the length of the intervals.